Hi class. In this lecture, I want to talk about some type of problem solving methods dealing with estimation, graphs, and then the last thing we'll do is we'll set up some mathematical models to help us answer questions or make predictions. That is. Okay, in this section, we have three objectives. The first one is we want to use estimation techniques to arrive at an approximate answer to a problem. The second thing we want to do is we want to apply estimation techniques to information given by graphs. And the third thing we want to do is we want to develop mathematical models that estimate relationships between two variables. Okay. First off, when we're talking about estimation, the process of arriving at an approximate answer to a question. Okay, so an approximate answer, there's three ways. First off is by rounding numbers. So we'll talk about how you round numbers in case you've forgotten. Using graphs, and then finally using these mathematical models. And that'll be the last thing. Okay, how you round whole numbers. So you look at the digit to the right of the digit where rounding is occurring. So for example, if I want you to round to the hundreds place, you're going to look in the tens place. So the second thing here, if the digit to the right, like in the tens place, okay, is 5 or greater, then you're going to add 1 to the digit to be rounded. And then you're going to replace all the digits to the right of that number with zeros. So we'll do some examples. And then second, if the digit to the right is less than 5, you do not change the digit to be rounded, but you replace all the digits to the right of that specific number with zeros. And then we use this symbol that looks like two squiggly lines, like a squiggly equals sign. This means the answer is approximately equal to approximate. Okay. So we're going to have this number here. So this is the world population. It's 7,476,242,056 people. That's the world population. All right, so I want to round this to the nearest 100 million. Okay, so what you're going to do to go to the nearest 100 million, you go to the 100 millions place. So you're going to look at this 4. You're going to look at the number to the right. It's a 7, okay? So since that number is greater than 5, I'm going to take the 4, and really what I'm going to do is I'm going to round it up. So I'm going to take the 4, I'm going to turn it into a 5, and then I'm going to replace all the other digits here with zeros. So what we're able to say then is the world population is approximately equal to 7,500,000,000, or I'll just say 7.5 billion. Okay, so the world population to the nearest 100 million is 7,500,000,000. So it's like we're rounding it here because, like, yeah, it's like pretty close to that. It's a little less, but we're just rounding it up. All right, so again, let's do another one. I've got the world population, and let's round it to the nearest millions. So you're going to go to the million place, which is the 6 right here. You're going to look to the right. You're going to see the number 2. That's less than 5. So I'm going to leave the 6 alone, and I'm just going to replace these all with 0. So I'm going to say the world population is approximately equal to 7,476,000,000 people. So we're just rounding down in this case. So here, what we're saying, like I said, the world population to this nearest million is 7,476,000,000. So we rounded down here. If I want to round to the nearest thousands place, or the nearest 100,000, again, I'll go to the 100,000s place. It's a 2. I'll look right here. It's a 4, so it's not 5 or more, so I'm just going to replace these with 0. And to the nearest 100,000, the world population is roughly 7,476,200,000. Okay. So hopefully, I know this was a quick example of rounding, but hopefully, like it makes sense, or you remember this from your previous, like high school or lower. All right, so let's do just another one. The first 7 digits of pi are 3.141592. So let's round pi first to the nearest hundredths. So, we know that in terms of decimals, this is the tens, the hundredths place is right here. Okay, so the hundredths digit where rounding occurs, I'm going to go to the 4. You look to the digit to the right is less than 5, so we do not change the digit. So when you have a decimal, all we do is we drop these. We don't replace them with zeros. Okay, so how it works with the decimal is a little bit different. Okay, so we just say the number pi is approximately equal to 3.14. So with the decimal, instead of replacing these with zeros, you just drop them all. So let's round it to the nearest thousands, tens, hundreds. Here's the thousandths place. Well, the digit to the right is 5 or greater. So I'm going to take this 1 and I'm going to change it to a 2. And I'm going to say pi to the nearest thousandths place is 3.1, or is approximately equal to 3.142. So when you have a decimal, you round roughly the same way. Okay, you just cut the zeros off, or you just cut the values off instead of replacing them with zeros. All right, let's do another estimation by rounding. All right, so this is just to help you get like an idea of how much things cost. Okay, so you purchase bread at the store for $2.59, detergent for $5.17, buy a sandwich for $3.65, an apple for 47 cents, and you buy a package of coffee for $8.79. Okay, so the total bill here was $24.67. Right, so is this amount reasonable? Okay, just to see. All right, so to check, what we're going to do is we're going to round all the prices to the nearest dollar. So this bill was $24.67. So this seems high compared to the $21 estimate. Okay, so let's add this up. So if I take bread and I round it to the nearest dollar, so 2.59. Okay, I look at the 5. I'm going to round this to roughly $3. The detergent, right, 5.17. When I round this to the nearest dollar, that's roughly $5. The sandwich, when I round it to the nearest dollar, $3.65, that rounds to roughly $4. The apple, all right, since it's less than 50 cents, so there's the number here is less than 5, I'm going to round this down to $0. The coffee, $8.79, I'm going to round up to $9. So 3, 5, 4, 0, and 9 rounds up to $21. Okay, so yeah, that seems a bit high to get to that bill. All right, so adding the prices of all 5 items actually gives the true bill to be $20.67. So like this type of estimation you can quickly do in your head, and you can determine, wait a second, something funky is going on with the bill. So like, for example, maybe they counted the sandwich twice or something. Like, so just so you can do this quick and see. All right, let's talk about circle graphs. So circle graphs, also called pie charts. So how a whole quantity is divided into parts. Okay, so circle graphs are divided into pieces, and these pieces are called sectors. So let me show you an example of this. All right, so the figure on the next slide shows a circle graph that indicates how Americans disagree as when, quote unquote, old age begins. All right, so like, when do Americans consider old age to begin? That's what this pie graph is going to show, right? Because it's like a subjective value. I don't even know how you might decide when old age begins. So in a survey of Americans, this is how they defined it. 32% of Americans say it's the decline in mental function. 41% say it's the decline in physical ability. 3% call it becoming a parent. 9% call it retirement. 1% call it, I would say, I don't know when it begins, and 14% old age begins when you reach a specific age. Okay. So if you were to quickly add this up, 32%, 41%, 3%, 9%, 1%, 14%, these all sum to 100%. So the circle represents 100% of the responses. All right, so keep this in mind, right, these numbers here. So let's ask a question. According to the U.S. Census Bureau in 2016, there were roughly 219,345,624 Americans 25 years and older. Okay, so that's just the number of Americans 25 years or older. So assuming the circle graph on the previous slide represents this age group, so meaning that nobody in that slide was 25 years or younger, okay, or younger than 25 years. Here's the first question. Use the appropriate information displayed by the graph to determine a calculation that shows the number of Americans 25 years or older who define old age by a decline in physical ability. And then let's use rounding to find a reasonable estimate of this calculation. All right, so here's how we're going to do it. We know the total number of Americans 25 years or older. Looking back, we know that roughly 41% of Americans say old age happens when there's a decline in physical ability. So use this determination, or use the use the to determine a calculation to show the number of Americans 25 years and older who define old age by decline in physical ability. So I want to use this graph to define that number. Okay, so the circle graph, as I said, indicates 41% of Americans define old age by decline in physical ability. So all you're going to do to find the number is take 0.41, taking that percentage and turning it into a decimal, and multiply it by the total population. Okay, so if you have a number, total number, and you want to figure out, oh, hey, 41% of, what's 41% of that number? You take the 41, you turn it into a decimal, and you multiply. So to do this, all right, that number, whatever that comes out to be, will be the number of Americans who define old age by a decline in physical ability. All right, but let's actually show you rounding to find a reasonable estimate for this. All right. So what I'm going to do, how I got to this number here, is I'm going to take this 0.41 and I'm going to round it to the nearest tenth. So 41%, I'm going to say roughly 40%. I'm going to take this number and I'm going to round it to the nearest 10 million. So here's the 10 million spot. I look to the right. That 9 is going to turn the 1 to a 2. So instead of saying there's this many Americans 25 years or older, we're going to say, hey, look, there's roughly 220 million. So taking 0.4 by 220 million, you're saying this. Roughly 220 million, you're saying this. Roughly 88 million Americans aged 25 years or older say, quote unquote, old age begins when there is a decline in, as they said, physical ability. A little bit easier, like you could maybe even do this in your head, instead of figuring out what exactly this is. And you'll see that it's a reasonable estimation. Like if you were to take this and plug it into your calculator, you would get pretty darn close to this number right here. So we're saying approximately 88 million Americans aged 25 years and older define this old age by a decline in physical ability. Okay. Let's get away from these circle graphs and now talk about bar graphs. So we're going to do estimation with bar graphs. So bar graphs use a vertical or horizontal bar to represent each item. So the length of the bar determines the amount. Okay, we can use bar graphs to make predictions. And the bar graph on the next slide shows the life expectancy in the United States by year of birth. Okay, so this is what we're saying. I have it by males and females. All right, so just quickly looking at life expectancy here, you're seeing that females actually have a higher life expectancy than males. And just by their birth year. So people born in 1950, if you're born in 1950, males expected to live to be 65.6 years, and females expected to live to be 71.7 years old. And it's gone up over time. And then when you get to by 2020, this is what we're saying. Males, if you were born in 2020, are expected to live to be 77.1 years old, and females are expected to live to be 81.9 years old. Right, and then also you can see that the bars are for other various years. All right, let's estimate a man's increase in life expectancy and round to the nearest hundredths of a year for each subsequent birth year. Okay, so I want to estimate, basically, this is what this is saying. On average, how much has life expectancy gone up for men each year? Okay, for each year. Well, to do this, you're actually going to need to calculate the slope. So here's what you do. You look in 2020. In the year 2020, life expectancy for males are going to be 77.1 years. So that's my first value I'm interested in, 77.1. And then I look at the first year I had, 1950. Well, life expectancy for men were 65.6 years old. So I'm going to find that subtraction. All right, but that's just going to give me the total difference. So to find it by year, I'm going to have to divide that by the difference in the years as well. So 2020 minus 1950 ends up being roughly each year, okay, since 1950, this is what this is saying. Each year since 1950, life expectancy has gone up approximately equal to 0.16 year. So for example, if somebody was born in 1951, a male, their life expectancy is not 65.6 years, but 65.6 plus 1.6 years. okay, because life expectancy is going up each year. All right, so for each subsequent birth year, what we're saying here is a man's life expectancy is increasing by approximately that 0.16 per year. All right, let's estimate the life expectancy of a man born in 2030. How the heck would we do this? Well, here's what you're going to do. You're going to take the first year you have, right? So the first year, so someone born in 1950, their life expectancy was 65.6 years. But here's what we're saying. Look, every year since 1950, life expectancy is going up roughly 0.16 years. So 1930 is 70 years since 1950. Like to get from 1950 all the way to 1930, you have to add 70 years. Well, to find out how much life expectancy has gone up over 70 years, you take the 70 and multiply it by the 0.16 life expectancy is going up per year. Well, that means 0.16 times 70 is roughly 12.8 years. So since 1950 to 2030, life expectancy for males has increased 12.8 years. So 12.8 years plus what it was in 1950 gets you 78.4. And that makes sense because in 2020 it was 77.1. Now we're saying another 10 years is going to be 78.4. So an American man born in 2030 will have a life expectancy of 78.4 years. Not too bad. All right, let's talk about line graphs. So line graphs here are often used to illustrate trends over time. Okay, so some measure of time, such as month or years, frequently appears on the horizontal axis. So this is the horizontal axis. It's like a flat line. And amounts are generally listed on the vertical axis. Right? Points are drawn to represent the given information, and the graph is formed by connecting the points with line segments. All right, so let me give you an example. So the line graph here, to the right here, shows the percentage of U.S. college students who smoke cigarettes from 1982 through 2014. So what this is saying is in 1982, right here, 24% of college students smoked cigarettes, and then by 2014, it was down to this number, whatever is roughly in there, somewhere between 12 and 16%. So let's find an estimate for college students who smoke cigarettes in 2010. Okay, weird. So how the heck are we going to do that? So look for 2010 on the horizontal axis. Notice how it goes from 1982, there's a dash, then 1990. What that means is this represents the year that falls right between these two, which is 1986. So to go from here to here, here to here, here to here, here to here, and so on is every 4 years. So here's 2006, then that means 2006 plus 4 years, right there, that gets me 2010. So the first thing you're going to do is you're going to find the 2010 year, and you're going to shoot up till you get to that point right there. So then the value on the vertical axis, shooting all the way over, like this, all right, is approximately midway between 16% and 20%. So this is what we can say then. In 2010, approximately, because we don't know the actual value, we're just kind of eyeballing it, approximately 18% of college students smoke cigarettes, which is bad. It should be a lot lower. Okay, so again, we got this line graph that shows the percentage of U.S. college students who smoke cigarettes from 82 to 2014. In which 4-year period did the percentage of college students who smoke cigarettes decrease at the greatest rate? Like what 4 years did it fall the most? Anyway, so just looking at this, you can kind of like eyeball it and see from here to here, it has like the biggest drop. Okay, so this is the steepest of all the decreasing lines. Okay, that means that it indicates the greatest rate of decrease. So this right here is the steepest of all the decreasing segments, indicating the greatest rate of decrease was years 2002 through 2006. Like maybe that was the big push that said, smoking was really bad. And it got out there on television and ads, and those were the years that we saw the steepest decline. All right, so again, the next question here, using that same graph, in which year did 30% of college students smoke cigarettes? So what you're going to have to do this one is I'm telling you that 30% smoke cigarettes. So on the vertical axis, you're going to go up and find 30%, which is right here. Then what you're going to do is you're going to shoot over until you hit the line right here. Well, I see that point there is roughly 30%. So then to figure out what year that is, I'm going to go down on the graph and see what year that happens. So the year when this happened was 1998. So in 1998, wow, this is crazy. 30% of college students were smoking cigarettes, right? That's unfortunate. That's a little sad. All right, let's talk now about modeling here. Okay, so let's talk about modeling. And what modeling means is we want to fit a mathematical formula to describe an authentic situation like we have here. All right, so this is modeling the cost of attending a public college. So what I want to do is I've got this bar chart here, and it says the average cost of tuition and fees at public four-year colleges. Okay, so like in 2000, the average cost to attend a public four-year college was $3,349 a year. That was how much, I actually went to college, was a freshman in 2000. That's pretty much roughly what I was spending per year to go to my four-year college, public. And then look what's happening, going way, way, way up. So by 2016, it was 9,410. So I want to estimate the yearly increase. Okay, so that's going to be the slope. So that's going to be the same formula. Now, forgive me, I'm going to go back in my slides real quickly. That's going to be the same formula we used here. Okay, this is the change in the value you're interested in divided by the change of the year. So going back to do this, all right, the approximate increase is how much it's gone up every year. So take the final value you have. I have $9,410 and subtract how much it was from your first value. Okay, so 9,410 minus 3,349 gets me $6,061. Okay, so from 2000 to 2016, it's increased $6,061. All right, but that's the total increase, but how much per year? Well, the difference in years, 2016 minus 2000, is 16 years. So to find the average per year, you divide these two numbers. You get $378.80, which I'm going to round. So I'm going to say that's approximately equal to $379. So what we're saying is basically every year, all right, we're estimating that the cost of attending college goes up $379 on average. Okay, so if you look at the increases per year, it's not always like that, okay? But that's just the average increase, okay? And notice, just to be careful here, that this is every 2 years. Okay, so don't be like, oh, from here to here it went up, roughly $600. Well, that's a 2-year change. All right, so the average yearly increase is $379. We got that. All right, let's write a mathematical model that estimates the average cost of tuition and fees. We'll call that T, the total cost, at public four-year colleges for the school year ending X years after 2000. So the variable X is years since 2000, okay, years after 2000. So when X is equal to 0, that's the year 2000. When X is equal to 2, that's the year 2002, so on. Well, the total cost is equal to, take your starting value, $3,349, and then you're going to add to it. Remember, it's going up on average $379 each year. Well, 379 times the number of years, well, the number of years here is X. So this equation here models how much the tuition has gone up. Let's use that mathematical model to project the average cost of tuition and fees for the school year ending in 2020. Well, 2020, here's my equation. First off, the total cost is this. 2020, if you go back, remember, X is years since 2000. So 2020 is 20 years since 2000. So I'm going to take that 20, and I'm going to plug it in for X. 379 times 20 gets me $7,580. Add to it how much tuition and fees were in the year 2000. Added to that 3,349. And we're estimating here, our model projects that the average cost of tuition and fees for the school year ending in 2020, wow, will be $10,929, which is a lot. All right, thanks, class.